Hi class. So another animation technique that I'd like to briefly cover is particle systems. Particle systems are really fun and they're really great. I think you're going to enjoy this unit. So here's the approach. First we model this a large set. Maybe large, doesn't have to be large, but typically the whole point of a particle system is you can scale it up. So a large set of objects in space. Now, because it's a particle system, these objects are abstract. Imagine an invisible point in space. You can draw something on top of it, but it doesn't matter at this point. You just have this point, this particle, in space at a location probably. And usually there's a large set of them. They're all very similar. So you basically define a few set of properties and you scale it up to many, many particles. Here's my space, and you can imagine I'm putting a bunch of particles in my space. And they're all really similar, okay? But each one, they act on their own. And that might seem strange, like we're not creating a new program or something, but they all act on their own. They're given a rule set and each one locally decides what it wants to do. This is really important for particle systems because when you try to model things top down and go, okay, you do this, it becomes very complicated very quickly. But if you can just say, forget everybody, you have a rule, don't collide with your neighbor and go in the same direction as everybody else. That's a rule you can solve locally. And then if everybody solves these local rules, you have this global behavior coming out of this. So each act on their own, and each is given a rule set to follow. It can be the same rule set for everybody. There could be variations. There could be randomness. It doesn't really matter. So, yeah, particles can also be possibly limited in lifetime. What that means is they can die. So the system that creates the particles has to be dynamic in that they can die, they can be removed, and they can be generated. So it's dynamic. Okay, on the fly, delete some, add some, delete some, add some. Okay, so they all have these actions, they're in space. Each particle, because of this, then each particle has its own state. This is where object-oriented programming really makes your life quite nice. You encapsulate a particle into an object, put all the important information inside, and it helps keep things clean. So for example, it might have a position, a speed, a goal that it's trying to do, and other properties. I mean, whatever you think up. So you envision now we have all these particles in space, and they're all going in their own little directions maybe, and they're moving around, and they're doing things. Okay. The whole idea behind a particle system is you set it all up. You set up the states. Okay? You set up the rule set. And you set up your if you've set up your states the way you want and your rule set, the goal is your desired behavior actually comes out of that. It emerges. And so this is really where the magic of particle systems comes in. And this is called, funnily enough, emergent behavior. And this is kind of, the sum is greater than the pieces type thing. If I just have these simple agents, you give them simple rules, and you push go, you might get some really cool stuff coming out of it. The classic one that really popularized this approach is flocks. So there's a famous algorithm called Boids, like birds, Boids. Okay, so this is flocks or swarms. It's a classic behavior that we'll see with particle systems. The idea is we can model natural behavior. Right? Now birds are pretty smart, but other animals like insects, flies, mosquitoes, they all have this swarming behavior. If they actually move in a very natural, organized fashion. but they're not very smart. They don't get together and converse. Even birds who are really smart, they don't get together and go, yes, let's fly in a V. All right. They don't do that. They each have their own little rule they follow, and the whole behavior emerges. Bats flocking in the night, they all have their own little rules they apply, and the resulting behavior emerges from these simple rule sets. Okay, that's really cool. We've seen this already. We saw in our Batman bats example, that was a particle system. It was a procedural particle system. They set up the rules and the bat behavior emerged. We also saw in the Lion King example with the antelopes. These are particle systems. Cool. So I'm going to get to some examples, but first, before I go over the example, I want to introduce the basic programming paradigm that you use with particle systems. So this is not, hard and fast rule, but it's pretty much any particle system you make will follow this pattern. One, of course, you set up your initial setup of particles. And up here, you might say, okay, I'm going to put these particles as 1, 2, 3, just say 8 of them, whatever. I'll put 100 or 800 or 8,000. You can make as many as you want. You put them there, and you say, this is your initial configuration. That's what you do. And then after we do that, then each frame we have work to do. Each frame, the first thing we do is we ask each particle to update their state. Okay, we say, hey, update, do your thing, check your neighbors, move in the direction, I don't know, you have your rule set, follow your rules. But of course, they're not threads, they're not working on their own. So each scene, we go, you do what you're supposed to do. We call those functions. After that's done, we check for dead particles. Particles that are marked for deletion. And we delete them. That's great. And then we also have to render our particles. Draw them, basically. Now, the examples I'm going to give really are one particle, one shape, like a triangle or whatever you'll see. But you can also imagine a meta shape where you have particles and you cluster them, and when you're doing something like smoke or something, a cluster could be represented as a dot, and how many items are in the cluster could be how dark the dot is or how transparent it is. And the more in the cluster, and you could use an octree or a quad tree to organize this, and this unit has this many, so make it this dark. So you can render them one particle per shape, but it doesn't have to be that way. And also, of course, new particles can be created. They can be generated. They can be generated randomly or often from a specific location. For example, not example, but this is often called the emitter. In a video game, you have an explosion, a rocket explodes, stuff comes out, that's the emitter, okay? I'm going to jump over to some demos now. Demo number 11 first. Let's demo 11, and I'm going to demo 12 at the same time. Okay, so I'm going to first demo this particle system. This is actually from the processing website. Go check it out. It's really nice that they provided this. So they create this particle system. This is nothing fancy. It's an object that's in here, and I'll get to it in a second. We set up we set up our canvas. We create a new particle system, and all that this is it tells it the emitter location where the particles start from. Each draw cycle, we clear our background, we add one new particle, and we run our particle system. It's easy. So let's go over to our particle system. The particle system is just an array list. It's just a list of particles, okay? And particles a type I'll get to. But it's just a list of particles. When we create a new a particle system, we just record the origin of the emitter, and we save that as our origin. And then if someone adds a particle, we just make a new particle, add it to our list. Now, when the draw function asks the particle system to run, this is what we do. We go through every particle in our list, we grab it, we tell it to run, we tell it, do your job, update it. If it's dead, we remove it. Cool. You might have noticed that it works in reverse order, and that's just because they're deleting things as they're iterating through the list. This is bad form. They should be using an iterator, but I'm too lazy to fix the code. Right, so particle system, each time we check each particle. You do your job. Are you dead? All right, we'll delete you, right? That's it. Now the particle here, each particle has their own position, their own velocity, their own acceleration, and a lifespan. And we'll get back to the lifespan. So when we create a new particle, here's the location, it creates some basic acceleration. It creates an initial velocity in a random direction. It's moving in a random direction. It copies our position. Oh, and it has a lifespan of 255 frames, 255 ticks. After that lifespan, it'll die. So then when our particle system asks us to run, we update and then we draw. Our update function, we add our acceleration to our velocity. We've seen this pattern before. And then we add our velocity to our position, so it's accelerating. And then we remove one tick from our lifespan. That's it. And then drawing is standard stuff. And then we're dead if our lifespan is less than 0. So what I want to highlight here is we're not modeling this grand scheme. We're modeling everything from the bottom up. It's a grassroots style of modeling. So we say, hey, we have these particles. Each one, all that it does is it adds some acceleration and velocity, and it ticks down. After so many ticks, it dies. And then it moves. That's it. We add the velocity to our position, it moves. We're done. Okay? That's all that happens. So really simple rule set here. But emergent behavior. When I have a particles and I create a new one in a random location, we add the where is it? Acceleration x and y. We add a downward y. This is processing, so positive y is downward. We add a downward y acceleration and no x. Gravity. Okay. Things are going to come out and then fall down. So we add a little bit of gravity to each particle. We just, very simple system. And look at how complex this behavior is. If I asked you, hey, program this, it's confusing and you get overwhelmed. But with a particle system, all we have to do is go, okay, it starts at a random velocity. Each frame, we add a little bit of downward y acceleration, gravity, and then that's it. We update it by adding the acceleration to our velocity, the velocity to our position, and then after a while we kill the particle. Each frame we get a new particle. It's that simple, okay? So just a few lines of code and we get this really complex behavior. That's awesome. That's the emergent behavior we're talking about. So I'm going to move over to sketch number 12. It's a little more complicated, but I think it's a little more fun too. So this is written by another instructor, John Braco. He made this. It's pretty cool. And I'm not going to go over the code in too much detail, but I want to show you the pattern. We set up, and then in draw, what we do is each time we figure out how far away we are from the mouse, and based on how far the mouse moved. And based on how far the mouse moved, we create new particles. If it moved a lot, we make a lot of particles. One per unit. Okay? We add a new spark. We call them a spark. So based on how far the mouse has moved, we go through a while loop. Don't worry about the math there. If we move 3 units, we add 3 new sparks. We create a spark, we add it to our sparks collection. Sparks is just an array list. It's our particle system. Okay, cool. Done. And then each frame we're drawing here, each frame, all that we do is we iterate over our sparks collection, and then if there's a next one, we get our S. If it's dead, we kill it. Otherwise, we call update. We tell it to do its job, and we draw it. Same pattern. Inside Spark, we have a lot of math in here, but all this is really clever color. So it has a color, position, a velocity, acceleration, a size, a rotation, rotational acceleration, and a timer. This is lifespan. Tells you how long it has to live. When timer runs out, we kill it. So it dies, okay? We initialize, we copy all those things into our variables. No big deal. A new spark, a random color. We set a random position behind the mouse. Don't worry about the math. We give it a random acceleration and a random lifespan, which modifies the acceleration. And we give it a random size, random rotation angle. So again, this is all just crunch work. Nothing fancy here, just random parameters. Update. All right. We rotate. Our rotation accelerates. We update our velocity. We update our position. We reduce our life timer. So we can look into this math and you go, oh my God, it's rotating. But it's the same pattern. We update our position, we do our local job. Each spark just goes, I'm moving this way, right? And then render, we just draw, okay? We draw, the only thing I'll notice is alpha channel gets smaller as timer goes down. That's all. We draw a triangle. And if it's dead if timer's below 0, then we can delete it. So what happens? So what this does is we get this really cool effect here where if I click the mouse somewhere, it creates sparks behind me. Look at that. How awesome is this? Disney, right? This is like, I could write my name, Jim. This is awesome. Again, if I showed you this and said, hey, implement that, you'd be like, that looks really complicated. It is. But with particle systems, we get to focus on the underlying basics and let what we want emerge. We don't have to model this from the top down. Particle systems almost give us superpowers to make complex systems by playing with the underlying properties instead of the global model. All right, so this is a good spot to take a break.